Hi, I'm Sandy. This is Mike. We are 2 of 44 teachers that were selected to be part of NASA's simulation-based aerospace engineering teacher professional development program in the summer of 2011. We are going to share with you a lesson plan that we have developed for that called What a Drag: Accommodating Assumptions.
Again, I'm Michael Brune. I've been teaching in Emmett, Idaho for about 8 years, and now I teach the high-level math classes of calculus, trigonometry, pre-calculus, college algebra. I also teach some geometry in there. And I'm also the head of the math department for the school district out there in Emmett.
And I'm Sandy Powell. I also teach in Emmett, Idaho. At Emmett High School, I teach physics, chemistry, and algebra. And for Payette River Regional Technical Academy, I teach engineering explorations. I also serve as the science department coordinator for Emmett School District, and I'm on the board of the Idaho Science Teachers Association. During this 2-week session, we have been fortunate to work with John Davidson, a researcher at NASA's Langley Research Center. He has been working with the Orion launch abort system, and he's active in modeling and simulation, and he has been very helpful in helping us put together our program.
All right, we're going to take a minute and walk you through what he's been working on. This is the LAS, the Launch Abort System for the Orion multi-purpose shuttle vehicle. If you look at what's going on here, you can kind of see we have a very quick launch. You know, there's not a lot of thrust coming, a quick amount of thrust, or a lot of thrust quickly, is how I should say that. And at the top of the rocket, you can see there's small boosters going on that actually control the trajectory of the rocket and make it go through the rotation that it's going through right now, so that then the crew module can separate and the parachutes can deploy and they land safely. John's been working on this pretty severely, and he showed us some of the simulations they worked on. It was all very interesting to see and to take a look at. So we really appreciated that view and insight that he gave us. Another video?
Okay. Oh, yeah, video. As part of what he has taught us and shared with us, he also gave us the idea for our lesson, which is based on how the model rocket is similar, or the water rockets are similar to the launch abort system. We've got a short video that will show that.
There.
Okay. And this just quickly goes through how the water bottle rockets are similar to the launch abort system. As you can see, both of the launch abort system and the water rocket have a very short thrust phase, and then they're more or less unguided or until they reach the top of their parabolic trajectory. Because of these similarities and because of the inexpensive materials required to run a water rocket simulation or water rocket activity with students, we felt that this would be a really good activity that could be extended to go into the modeling and simulation fields that we have been talking about. So let's talk about our lesson overview and just guide you through how our lesson relates to how the lesson is set up and what we'll be doing there. So first of all, we know that engineering may start with one problem, but there are many possible solutions. Models and simulations can be used to help find the best solution, but not all simulations are created equal. The simulations are actually based on what the maker of the simulation felt were the most important assumptions, and each creator of a simulation may make different assumptions. So what we are going to do for our lesson is take a look at the Euler method of integrating as you look at a ballistic trajectory, especially one that involves drag. We are then going to model that using some simulation software and then create what's called a Monte Carlo simulation, or a simulation of possible results based on varying assumptions. Then, to finish this up, we're going to have an engineering challenge where the students will be given the task of creating their own model rocket or their own water bottle rocket that needs to meet specific criteria, again based on the launch abort system, where there will be a specific distance we need that to fly and a specific time of flight range that it must fall into. The grade level this is for are 10th to 12th grade calculus and physics students. The student prerequisites are they need to have had some experience with ballistic equations and unit conversions. The content focus is the ballistics with drag, assumptions that are made in simulations, the Euler method, Monte Carlo simulations, and of course the engineering process.
And the learning objectives for the students will be for them to solve ballistic equations involving drag using the Euler method for integration. Okay, to vary their default values to create a Monte Carlo graph using simulation. To use the engineering process to solve a complex problem. Okay, compare the results of the simulations with experimental testing. And to communicate those results effectively with one another.
So here's our procedure. We're going to start on day one with a pre-assignment or a requisite skills web quest. This will be done in the computer lab, and that will involve students understanding what is the center of gravity, what is the center of pressure, and then they will be looking at two ballistics equations, ballistics-based simulations. Then they will be looking at 5 different simulations of water rockets. And each of these simulations will give them different results, even though they are inputting very similar values. The reason we chose to have them look at different simulations of the same thing was to give them the idea that different values can be given based on the different assumptions that may be made. After they've finished this web quest, then they'll go on to day 2.
Day 2, we're going to take a look at the Euler method for integration. And we've created a worksheet for the students to work through that does break down the Euler method. Because as we look at the effect of drag and gravity upon the trajectory of a rocket, that drag and that gravity is going to have a negative effect on the velocity of the rocket. And so to look at that, we can't just look at the rocket's trajectory as an initial condition taking off and going for eternity into the air. It's going to slow down. It's going to slow down in ways that we can't predict on a large scale, but we can break down and predict in small pieces. So by breaking our time segments into really small pieces and analyzing the trajectory in small pieces, we can really get a good idea of how drag is going to affect the trajectory of the rocket. Okay? And in this sense, it is integration. We're taking, using the Euler method, the chart's going to help the students organize that information so they can see how this all fits together and get that process figured out. So we'd like to take a minute and take you through what our simulation is going to look like. Because once the students have completed the Euler method together in class, they've done that exercise, they've done it by hand, they now understand how that fits. Well, now we're going to move into creating lots of sets of data, lots of rocket trajectories based on differing assumptions. Whoops. Let's get to the right worksheet here. All right, so what we've done is we've created this Excel spreadsheet. And in the Excel spreadsheet, we do have a lot of information provided. And the green cells, you can kind of see those are ones that the students would be able to vary to fit their conditions. Okay, and down at the bottom you can also see the default conditions, and those are also changeable to fit the situation that maybe the teacher wants to investigate to begin with. But this is just the beginning experimentation of Monte Carlo. All right, so to create our experiment, our plan is to have the students start with initial conditions. So our initial condition is an air pressure of 65 psi, or excuse me, that's probably not the initial condition we want. Let's see if I can go change that. We're going to start with an air pressure of 25 psi with about 250 milliliters of water. Oops, there we go. So let's change that data, which gives us a velocity of 72. Thanks to John Davidson for helping us calculate that velocity. That took a little bit of work and some doing on his part, so we sure appreciated that. The drag coefficient is also programmed in there. We did a little wind tunnel experiment to arrive at that drag coefficient of 0.31. All right, so based on this initial data, we can see in the yellow box that the downrange distance expected would be 76.5 feet, and the elapsed time would be about 3.49 seconds, and that's depicted in the graph as well. All right, so if you look at our table data, we've actually gone through and done some of this simulation. The blue dot represents that nominal case, that initial condition, and where we'd expect the rocket to land given that initial condition. All right, so now what we're going to do is have a little simulation. To figure out what the percentage change is going to be, we're going to have the students roll dice. And for the air pressure, to arrive at the error percentage, we're going to roll the dice, we're going to multiply the values together, and we're going to enter that percentage into our Excel document. The penny is going to represent whether that value is positive or negative.
Negative.
And so we have a negative 10 that we're going to put in for our percentage change. So we got a negative 10 there on our air pressure. So we're down to 90 psi. Looks like we have...
And negative.
Negative. So negative 20 for the volume of the water. So negative 20% change on the volume of the water.
And, sorry. Okay. Positive 24.
This would be positive. Okay. For the angle measure, because large variance really creates a lot of issues. Oh, this is a really old one.
Yeah, this is really old.
All right, so I guess we're going to vary the drag coefficient. Drag coefficient, if we do a positive 24% change, okay, then we arrive at all our new conditions. Okay. So let's see. I've got to put these back to where they should have been. And we're back to normal. All right, so now we've got new data. We can see that our air pressure ended up being about 22.5 psi. So I'm going to jump up to the air pressure, go 22.5 psi for my new air pressure. The volume of water has dropped to 200 milliliters, according to this change in condition. And my drag coefficient is down to 24, just allowing for some error in our drag calculation. Okay. Based on that data, we get a little bit different chart. We see that our elapsed time, or excuse me, our distance downrange is about 3.67 feet, and our elapsed time is 0.99 seconds.
What? Ooh. Okay. And so we plot that.
So we plot that point on our graph.
Okay.
And then the student would continue this and build points through about a 20-minute segment of a period. And we would have them doing this plotting and actually have that graph on transparent paper, so that after all the students have tabulated all their data and every little group has their data collected, we can take all that data, put it all together to get a whole bunch of Monte Carlo points, put that over on the overhead, and kind of look and see where is this data varying, how much data can we expect the students to see in this launch experiment based on our degrees of change and the error that we're allowing in the experiment.
Okay. Then we'll go into days 4 and day 5, which are the engineering project. Day 4 will be spent in the computer lab. They'll get a request for proposals, which is a request for a new design of a water rocket, and this design will need to meet specific criteria. As was mentioned before, because of the importance of making sure that the astronauts get away from the rocket safely and quickly, we're going to try to have a specific distance we need to have away from the launch pad, but not too far away because we want to make sure it's a water landing. And then we're also going to restrict the time of flight. It will need to be greater than a certain amount of time to make sure there's time to deploy the parachutes, but less than another amount of time to make sure that we have that the trajectory control rockets do not burn out or run out of fuel. So day 4 will be spent in the computer lab designing the rocket. Day 5 will be spent in the classroom building the rocket.
And then day 6 is where we actually launch the rocket. So we have a couple of rockets here we can show you that our mentor actually built for us and took the time to do that. So, you can kind of see there's different fin design applications we can try. We have the launcher here, and there's different launcher systems that can be built, although we're including the launcher system that's in the rocket handbook that NASA included. But this one is kind of interesting, so I'll show you real quick what we've got here. This one's got a nice little guide, different kind of tail fin on that one. What he's used is these little zip ties to help hold that nose of the bottle down. And they work fairly well, get a nice even release, and we get a pretty decent trajectory off the rocket. And to change angles, we just lean it, put some wood under there, measure the angle with some kind of tool, probably download onto a cell phone or possibly an iPod to measure that angle. All right, but what we're looking for is, do the students get the range that we wanted them to get? So after they launch the rockets, they're going to collect data for what their launch was. What was their time of loft? What was the distance downrange that they got for all 3 to 5 of their launches, depending on the time that it takes? We'll give them as many launches as we have time within that period. We're assuming with groups of about 10 groups of students, we're probably talking about 3 to 5 launches. But again, they'll collect that data, they'll include that data on their Monte Carlo with all the other points they've collected throughout the process of designing their rocket, deciding how they want their rocket to blast off, the conditions they're going to use. And now they plot that against what they predicted the behavior to be, and they'll use that data as they move on to the next step of the process.
And that next step of the process happens on day 7 of the project. Now, day 7 may not come directly after day 6. In fact, we suggest that a couple of days are given between days 5 and 6 and between days 6 and 7. And those are days that can be spent doing other normal class activities. This is to give the students some out-of-class time to build their rocket and then to take the data that they received from their rocket launches and put together a quality presentation, because their presentations will be graded and will be presented in front of the class. Some of the things that we are looking for in these presentations will be to look at their Monte Carlo graph. Do they have sufficient points to indicate that they have actually really worked to figure it out? Did they plot the nominal value, and did they plot their actual values on their Monte Carlo graph? Were they very clear in where the Monte Carlo simulation information came from? Which of the simulations did they choose to use and why? Or did they look at a variety of simulations? Did they use the given Excel graph that Mr. Brune created, or did they choose one of the online simulations? And again, an explanation, a very clear explanation of why they chose what they chose and how they came up with the values they put into the simulator to get their Monte Carlo results. So those are things that we'll be looking for, as well as the clarity of their presentation and how well they explained what they did and why. And that takes us through the procedure for the actual lesson. So then we need to talk about what resources are we creating for the students. They will have the requisite skills web quest worksheet. They'll have their Euler method worksheet, the Monte Carlo graph, the request for proposals, the rocket stability worksheet, and the proposal presentation score sheet. The assessments will be the requisite skills worksheet, the Euler method worksheet, the Monte Carlo graph, and the proposal presentation score sheet. And as you can see, those assessments are tied directly back to the student prerequisites and to the initial learning objectives.
As we move into the next steps of this process, we hope to teach this combined. So hopefully we can break our classes into the groups together, have students that are in both physics and calculus, and be kind of the project managers for the situation, where they have to communicate between the group they're in calculus class and the group they're in their physics class, and take the information back and forth. And the calculus class will take care of the calculations and the engineering end. Okay? And then the physics class may be more involved in discussing the formulas we're using as we do these calculations, and the modeling end, and then the creation. And then both classes together doing the launch and being part of it and enjoying that process. And we also anticipate further collaboration with one another, and this being kind of a catalyst to that collaboration. And that'll be a great thing and a great resource for our district.
We will also, as both of us are department coordinators for the district, we will be able to share with our district what we have learned here and what we've created. We also will be presenting at the Idaho Science Teachers Association and the Idaho Council of Teachers of Mathematics Conference this fall. Those will be combined in our state this year, and we'll be involved in that. We also have some other opportunities that we are looking at to possibly share what we have learned here. And I need to tell you, this has not been a drag. This has been a wonderful experience, and we really have enjoyed it.
Yeah, we certainly have. You know, and we really hope that our students get a great exposure to the engineering process through this, just what we've created here. We think that through the modeling of the simulation and touching on that and seeing how different points are arrived at, predicting behavior, seeing then in actuality, does the predicted behavior actually meet the experiment, we're going to give our students a good resource and insight into what the engineering process looks like and how we accommodate these assumptions that we're dealing with. You know, we really want to thank our mentor, John Davidson. He was a huge help, always available, gave us tons of time, brought stuff that we didn't even anticipate him bringing, his resources, and it was just a huge help. And thanks also to all the people here at NASA. It's been a wonderful experience, very accommodating. Everything has been extremely easy, more resources than I know what to do with at this point, and I just really look forward to the opportunity of getting a chance to dig into those resources, look at the lesson plans other people have provided, and make use of all this great material that's been given to us here. So again, we thank you all for all the time and effort you put on our behalf.